Okay, so, right. Setup is, we start with a group, and then we form the automorphism group. It's a group of automorphisms, bijective homomorphisms. It's a group under composition. And we have this map that takes an element of the group G and then produces the corresponding inner automorphism. And that map itself is, of course, a group homomorphism from G to its automorphism group. But then once we do this construction, we have a map from G to Aut G. We could do it again. We could get a map from the automorphism group of G to the automorphism group of the automorphism group of G, and so on. So the question is, what happens when we just keep doing this over and over forever? So to start answering that question, let's look at some examples. Right, so easiest example, you start with a trivial group, and then everything's trivial forever. The automorphism group of the trivial group is trivial, the map has to be the identity, and that's the whole sequence. Okay. Next less complicated group, Zeeman2. That also has trivial automorphism group. So we're right back where we started after one stage. Okay. Next most complicated group, cyclic group of order 3, has 2 automorphisms. So it takes us an additional step. We already figured out what happens when we get to Zeeman2, so we're done after that. Okay. And so maybe if you were being really hasty, you might conjecture at this point that eventually every group will get to the trivial group and then it'll be the trivial group forever. But that's not true, because the next example shows there's a group of order 4 where that doesn't happen. So we have this group of order 4 whose automorphism group is bigger than itself, has more elements, which I guess is kind of what I would expect generically. And we have this map from this group of order 4 to S3. S3's automorphism group is itself, and not only is S3's automorphism group isomorphic to itself, but the natural map that we have from S3 to the automorphism group of S3 is an isomorphism. So this sequence doesn't stabilize at 1, but it does stabilize in the sense that eventually all the maps in the sequence are isomorphic. Okay, and there's another group of order 4. So for completeness, here's that other small example. Goes right to Zeeman2. All right, so we saw that it doesn't always get down to 1, but in all of these examples so far, the sequence does eventually become all isomorphisms. So if you're just tuning in, the construction we're doing here is we take a group and we have the natural map from the group to its automorphism group by inner automorphisms. And we just keep doing this construction. We keep looking at these maps. And in all of these small examples that we've looked at so far, eventually we reach an isomorphism. And as soon as one of these maps is an isomorphism, all the following maps have to be isomorphisms. Because once the map from S3 to S3 is an isomorphism, the next map is the same one. So they're all isomorphisms. Okay. So that seems to happen every time. It doesn't happen every time. So here's another small group. The dihedral group of order 8 is isomorphic to its own automorphism group, but not via the natural map. So this the way we can tell is that the kernel of this natural map is the center of the group, and D8 has a non-trivial center. So this map is not injective, but nevertheless all the groups are the same. So we get this like non-stabilized version. Well, I don't know. Maybe we should say this stabilizes. Maybe we shouldn't. I claim we say this doesn't stabilize because the maps are not isomorphisms. So with that convention, this sequence doesn't stabilize. We just get D8 to D8 to D8 forever, and none of the maps are isos. It's kind of boring. Okay. But there is kind of a way to rectify this situation, which makes everything interesting again, which is if your sequence didn't stabilize at a finite stage, just take the co-limit of the sequence. So yeah, I will go and actually compute some of these co-limits and explain how these work, if not clear. But at least for now, bear with me, co-limits of sequences of groups exist. They're a thing we can do. And so we have this way to extend this sequence transfinitely past the finite indices to any ordinal. Okay. And then the next question we might ask is, even if this doesn't stabilize at a finite stage, is it eventually the case that for some ordinal, the map becomes an isomorphism? Spoiler, yes, that always happens. So it turns out for this D8 example, even though at all the finite stages, none of the maps were isos, the co-limit, the omega group, is the the group of order 2, and we already saw that that stabilizes immediately. So that example worked. Okay. And this transfinite sequence of groups is called the automorphism tower. And just to, like, I guess, be a little more precise, this arrow here isn't really one arrow at all. It's kind of representing the fact that we have maps from all of the previous groups to G omega. And they're all kind of compatible in a nice way. All right, so let's, I'll explain exactly how this example worked with the D8s. So pictorially, I'm going to draw D8 as 8 dots. And I'm going to forget the group structure. And okay, so it turns out that this map has a kernel of order 2. Here's the kernel. And that means it's going to map cosets to points like this. Each of these sets of 2 elements of D8 has to go to a single point. And pictorially, the way this looks is this one goes here, this one goes here, this one goes here, and this one goes here. So at the next stage, these what was these 4 different points collapse down to these 2 different points, and those 2 different points are both going to go here. They collapse down to 1 point. Okay. And likewise here, this one goes, I guess we said it goes here or something. But you know, the way I drew it isn't very important. The idea is just that when we form the colimit, the way that's actually done is by just taking the disjoint union of all these groups and then identifying 2 elements when I can produce one as the image of another via the natural maps. This is the correct notion in this case because the sequence is not just directed, it's actually a sequence. So what we can see from this picture is that there are kind of two classes of elements here. There's the ones above this line and the ones below this line. And the ones above this line always stay above the line. The ones below the line always stay below the line. And moreover, any 2 elements that are above the line eventually merge at some stage. Any 2 elements below the line eventually merge at some stage. But above the line and below the line never merge. So that this colimit here has 2 elements, Z mod 2. Okay. So that's an example of this colimit in generality. For most of the talk, though, the colimits will end up just being literal unions. So that's nice. Okay. So this is the theorem that I spoiled a little bit ago. If I take any group at all and I do this construction, I start doing the automorphism groups, and then I do the colimit, and then I do automorphism groups, and I do a colimit forever. Eventually, at some point, this stabilizes. I get an isomorphism, and then after that isomorphism, they're all isomorphisms. So okay, before we try to figure this out, if we want to know, okay, if we know that this already does happen, how could we try to prove it? We should look for something that happens in all these cases, and yeah, try to identify some common feature of this point where the groups stabilize. So if I have a group where the map to its automorphism group is an isomorphism, what that means is the map to the automorphism group is in particular injective. It has a trivial kernel. And the kernel of the map from G to Aut G is just the center of G, which you can compute directly. So the kernel of this map is the set of elements of G such that conjugation by G is the same as the identity. But if conjugation by G is the identity, that means this element, little g, commutes with every element of the group, so it must be in the center. Okay. So, so this is like a necessary condition. If it's going to stabilize at some group, it must be the case that this group has a trivial center. And something we could ask is like, is that enough? Is it enough to have a group with a trivial center? Must it stabilize? We saw an example where it was good enough in S3, I think was that example, and also the trivial group. These both had trivial center, and they both had isomorphisms to their automorphism groups. But that doesn't work in general, it turns out. For example, S6 has non-trivial outer automorphisms, which is just to say that S6 has no center, but the map from S6 to its automorphism group is not an isomorphism. It's injective, but the automorphism group of S6 is much bigger. Well, by a factor of 2, not much bigger. Okay, so that's kind of annoying. It's, you know, not a trivial problem, but at least it gives us some place to start. So we're going to consider centerless groups as our starting point. And the reason it's good to consider centerless groups is the following argument. If I start with a centerless group, then, okay, by what we said before, the kernel of this map to the automorphism group is trivial. So the map from G to its automorphism group is injected. But then if I look inside the automorphism group of G, inside this group G1, and I look for the centralizer of the image of the original group. So this is all the elements of the automorphism group of G, which commute with the inner automorphisms produced by G. You can go and write out what this means. Okay, so this is a set of elements of G1, where for all elements of G, if I conjugate the inner automorphism by this automorphism theta, I get the same inner automorphism back. And it turns out that this inner automorphism theta compose, or this automorphism theta compose I of G, compose theta inverse, is the same as I of theta of G. And the reason for that is just that if I do theta of I of G of theta inverse of X, well, first I apply theta inverse, then I conjugate by G, that's what I of G does. So that gives me G theta inverse X, G inverse. And then I apply theta again, which distributes. This is theta of G. And then the theta of theta inverse of X is X. And then this is a theta of G inverse, which is the same as theta of G inverse. And so conjugating the inner automorphism I of G by theta produces the inner automorphism I of theta of G. Okay, so from there, that changes this set to this set. Okay, those are the same set, I mean. And then rewriting this condition here, well, we know that the map I is injective, right? So because I is injective, if I of theta of G is the same as I of G, then theta of G better be the same as G. And if for all G and G, theta of G equals G, the map theta better be the identity on G. So this argument shows that the centralizer in the automorphism group of the image of G is trivial. But the centralizer in the automorphism group of the image of G is certainly bigger than the center of the automorphism group. Anything in the center of G1 would commute with everything in I of G. But there might be other things that commute with I of G. But since the only thing that commutes with all the elements of I of G is the identity, the only thing that commutes with every element of G1 is the identity. So G1 also has trivial center. Centerless, trivial center, I will use interchangeably. So this is like an interesting fact. It tells us that if we start with a centerless thing, we get an injective map to the next thing. And that next thing is also centerless. And that gives me an injective map to the next thing. And that next thing is also centerless forever. And the nice thing about that is now we can just kind of forget about all these maps. We have this like whole sequence of groups with maps, but now just by identifying each group with its image in the next group, we can just pretend these are like subset inclusions. Okay, which is like helpful, but also kind of confusing sometimes. And the other nice thing about this is that it turns the co-limit into a literal union. Once we've done this identifications, where every group gets identified with its image in the next group, the co-limit of that sequence is literally the union of all the previous groups. So that's helpful. Okay. And so here's like a little quick history of how this happened. So Zassenhaus in the 30s realized that this happens. If you start with a centerless group, the automorphism group is also centerless, and etc. And he had this question of, does this always stabilize? Is it always the case that there's some finite stage, because he hadn't done this co-limit thing yet? Is it always the case that at some finite stage, this subset inclusion is actually an equality? And in 1939, I don't know how to pronounce this German name, Violent? So if someone knows how to speak German, let me know. But they proved that the answer is yes. This always happens.
Wieland.
Wieland. Thank you. Okay, so in 1939, Wieland said yes. The proof that he gave is actually really complicated. Takes many pages. It's all in German, and has a lot of like really in-depth analysis of weird chains of subgroups inside centerless groups. So kind of an annoying proof, but valuable in the sense that it answered this question. And then it took another like 30 years for anything to happen. in the 70s, people started working on this for certain classes of infinite centerless groups. And so for certain special cases of infinite centerless groups, they were able to prove that this terminates at some finite stage, or maybe this terminates at some infinite stage. At that point, I think they had come up with this co-limit idea. But then in 1985, there was this really nice breakthrough by Simon Thomas that this actually does stabilize at some possibly transfinite stage for any centralist group you start with ever. His proof works for both finite and infinite groups, but the bound he gets for finite groups is lame. So Wieland said this stabilizes at in a finite number of steps if I start with a finite centerless group, and Thomas's proof tells us that a finite centerless group stops in at most some countable ordinal number of steps, which is much worse. But at least he does tell us that every centralist group stabilizes at some stage, even the infinite ones. So that was a new result. And this is going to be the result we spend most of the talk going through the proof of. Okay. And I promise we'll get back to why this actually answers the whole question. So notably, because Thomas proved this result in 85, once we know this is true, if we can just prove that every group eventually reaches a centralist group somewhere in its automorphism tower, then we're done, right? As soon as we reach a centralist group, then Simon Thomas tells us, oh, eventually that centralist group will stabilize. So, okay. So let's get into that proof. Here's the exact claim that he had. You start with a group with trivial center, you make this automorphism tower, then it stabilizes eventually, and he has a little bound for when it stabilizes. This bound here is in the case where G is finite, but that's the less interesting case because that was already proven, and there's a better bound in the finite case. But this bound is good. This is always. Well, okay, I should say G infinite. In the infinite case, that's a really nice bound. Well, I don't know, it's something. Okay. Right, so how did he prove this? Let's do it. So we're going to focus on the infinite case, so we don't have to like deal with whether or not our bound is omega 1 or the cardinal after 2 to the G. I should say what that means. This thing here is the next cardinal number after the cardinality of the power set of G. Hopefully that's right. So, yeah, whatever that cardinal number happens to be, that's what we're talking about there. Okay, and so in our case, this is the number that lambda is going to be always because G will be infinite. And so the first step in the proof, which we won't do, is just that the centralizer in any stage of the automorphism tower of G is trivial for all alpha. So this is really exactly the same as it was done in the finite case, which we saw the first stage of. So I'll rewind back there. Nope. Where was that? Here. On this page, we showed that the centralizer in G1 of the image of G was trivial. And it's not just true in G1, you could repeat this argument for G2. The centralizer in G2 of G is also trivial. And the centralizer in G3 of G is also trivial. And you can take the co-limit, it still works there, and you can keep going. So we won't do that argument, but it's true. It's basically just repeating that argument over and over. You get that the centralizer in any stage of the smallest group in the tower is trivial. Okay. And that's going to be a useful fact. But now we're going to look not just at the centralizer, but at the normalizer, which is bigger. So, or at least no smaller. So, okay, we're going to take some element in the normalizer of G inside some stage of the tower for alpha at least 1. And the definition of normalizer is that if I conjugate the subgroup G by the element phi, I still get the subgroup G back. And what that means is that this phi acts on the subgroup G by conjugation. Conjugating elements of G keeps them in G. So I have some conjugation action on G, and that gives me this map from this conjugation map from G to G, which is an automorphism of G, so some element of G1. And really, you can think about phi 1 as being just like phi restricted to G in some sense. So that's some element of G1. But the interesting thing about this element phi1, this automorphism of G, is that if I conjugate an element of the original group G by phi1, it's the same as having conjugated it by phi. And to go through this chain of equalities, we have to think very carefully about our identifications, so the upside of our making all these identifications is that we don't have to write down as many maps all the time. But the downside of all these identifications is that now we have to think about where all these elements are living and how we should be identifying them. So let's think through it carefully. First thing is, on the left-hand side, I have this element phi1, which is an element of G1. And G1 is a subgroup of G alpha. So phi1 can be viewed as an element of G alpha. And we're performing this multiplication on the left as inside G alpha. So like, have phi1 as an element of G alpha, I have G as an element of G alpha, that multiplication. Okay. Then next up, if I want to actually do this multiplication, what I want to do is take my element G, lift it up to its identified image in G1, and then do the multiplication inside G1. Because then all the elements phi1 and I of G and phi1 inverse all live inside G1, so that multiplication can be done as well. And so these are the same thing. If you like, this is just because G and I of G have been identified. It's G identified with itself. But what we saw before is that if I conjugate an inner automorphism by some automorphism on the outside, it just applies that automorphism to the inside of the inner thing. So this was the same argument from before, saying that phi1 I of G because phi1 inverse is the same as I of phi1 of G. You just go and apply both of those functions to a particular element, you'll get the same outputs. Okay, so that's this equality. But then I of something is identified with just that thing. So that's our identification again. And phi1 of G, by our definition of phi1, is precisely the conjugation of G by phi in G alpha. So what we're seeing here is that inside G alpha, conjugating an element of G by either phi or phi1 does the same thing. And what that means is that phi inverse times phi1 commutes with G. If you just we have this equals this, so pull this phi over to the other side, pull this phi inverse over to the other side, we have a phi inverse here, phi there, that would just equal G. So this tells us that phi inverse times phi1 commutes with G, but G was any arbitrary element of our original group like G0. So this means that phi inverse times phi1 commutes with every element of the group G. But we already know, well, I told you that the centralizer of this group G inside G alpha is supposed to be trivial always. So because this element here commutes with all elements of big G, but also it's the case that, so this commutes with all elements of big G, but the only thing that commutes with all elements of big G is the identity. This means that phi inverse times phi1 is the identity. And in other words, phi is the same as phi1. So that was all to say that if I take this element of the normalizer of G, then it restricts in a well-defined way down to G. And that restriction, when I then identify it back up in the whole big group, is the same thing I started with. Okay. And this shows that the normalizer of G in G alpha is the same as G1. So what we showed here, I guess directly, is that the normalizer is contained in G1. Every element of the normalizer came from some element phi1 in G1. And the converse is true as well. Every element of G1 is an automorphism of G. And when I conjugate that automorphism around some element of G, I'm just applying that automorphism to the element. So that'll be in the normalizer. Okay, feel free to stop me if things are confusing. So this is a nice thing. Okay, so that adds a new thing we've shown. We know now that the normalizer of G is G1. And next, we're going to look at the index of G1 inside G alpha plus 1. alpha plus 1 just to avoid some technicalities. So, okay, this worked for all alpha. So this index here is the same as the index of the normalizer because G1 and the normalizer are equal. So that's the same. But then the orbit stabilizer theorem tells us that this is the number of conjugates of G inside this big group, G alpha plus 1. So the normalizer of G is just the stabilizer of the conjugation action, and the index of the stabilizer has to be the number of orbits. Or sorry, the index of the stabilizer has to be the size of an orbit. So that's what I mean. And the size of an orbit here is the number of conjugates. Okay, so that's some group theory fact. This is the number of conjugates of G in G alpha plus 1. But then the interesting thing is that every conjugate of G that we find lives inside the smaller group G alpha, like the previous stage. And the reason for that is kind of the same argument we keep doing. We look at this, like, we take an element of G and we conjugate it by an element of G alpha plus 1, whatever that is. And then we realize this element came from the original group G. So this is really an interautomorphism of some element in G alpha. And then when I conjugate an interautomorphism, I just apply that automorphism on the outside to the inside. And so that gives me that this is an interautomorphism of x of G, whatever x was. And because x of G lives in G alpha, and I've identified x of G with I of x of G, then this resulting thing lives in G alpha. So what I showed here is that every element of G, when conjugated by anything at all in G alpha plus 1, lives inside G alpha. And as a result, every conjugate of the whole subgroup G lives inside G alpha. Okay. All right, so the interesting thing there is the number of conjugates. Well, every conjugate of G in G alpha plus 1 has an inclusion map from G to G alpha plus 1. And no two different conjugates can have the same inclusion map. The image of the inclusion map uniquely determines which conjugate we're talking about. So all I'm saying is the number of conjugates of G has to be at most the number of functions from G to G alpha. Each conjugate has an inclusion because it lives inside G alpha, and these inclusion maps are distinct for each of the different conjugates. So this is at most the number of functions from G to G alpha, and just by definition, that's the cardinality of G alpha to the power of the cardinality of G. So we have this fact. We've found the index of G1 inside G alpha plus 1. We have a bound for that in terms of the cardinalities of G and the cardinality of G alpha. And so what can we say? Now the cardinality of G alpha plus 1 itself is just the size of the subgroup times the index of the subgroup. So just multiply both sides by the size of G1, and we use our inequality. We get that G alpha plus 1 is less than or equal to G1 times, or the size of G1 times the size of G alpha to the power of the cardinality of G. But because alpha is at least 1 in this context here, the size of G1 is less than or equal to the size of G alpha. So I can just combine that in here. And then because G is infinite, the cardinality of G plus 1 is the same as the cardinality of G. Here I mean cardinal addition. So we have the same thing there. Okay, so that was not too bad. We saw that we have this bound here, that the cardinality of G alpha plus 1 is less than or equal to the cardinality of G alpha to the power of the cardinality of G for all alpha greater than or equal to 1. And then we could do a transfinite induction proof to show that for all alpha less than this lambda where we hope it's actually going to stabilize, the cardinality of G alpha is less than or equal to the cardinality of the power set of G. The way this works is, not too bad by transfinite induction. Here's the first 2 steps. The base case is, well, alpha equals 0 is easy. Alpha equals 1, I think you have to do another base case where you just show directly that the size of an automorphism group is at most the size of the power set of the group for infinite groups. And next up, for our inductive step, the cardinality of G2 is less than or equal to, by this inequality, the cardinality of G1 to the power of the cardinality of G. But the cardinality of G1, we already knew by the same inequality, is less than or equal to 2 to the power of cardinality of G. And then that just gives me a 2 to the cardinality of G squared. But if G is infinite, then that's the same as the cardinality of G. So by some kind of cardinal arithmetic there, that's not too bad. And that's like the finite inductive step. And you also have to do your like transfinite inductive step where you take the limit ordinal. But I promise that works too. There you have to use the fact that lambda is a regular cardinal, successor cardinal. Okay. But so I promise this works. For all alpha less than lambda, we have that the cardinality of G alpha is also less than lambda. It's at most 2 to the cardinality of G. So we're almost done. All we have to do now, so okay. Now we're just actually going to show that this map from G lambda to G lambda plus 1 is an isomorphism. And remember that it has to be an injection already. All these maps are injections. So all we have to do is show that this is actually surjective. So what I'm going to do is I'm going to take an element of G lambda plus 1, and I'm going to prove that it's actually in the image of this map from G lambda, that it is given by some inner automorphism on lambda, on G lambda. So let's do that. Okay. First step is this is the black box, where the set of ordinals less than lambda such that if I take this, it's okay. We have pi, which is an automorphism of G lambda. So let me draw that here. There's also these G alphas, which sit inside here. And the question is, when is it the case that pi restricts to G alpha and sends G alpha to G alpha bijectively? The answer is this happens not just at least once, but for an unbounded set of ordinals up before lambda. I've seen a proof of this. I probably can't explain it as well as people in the audience, but the idea is that this is what's called a smooth union, and there's something bijections of smooth unions for uncountable regular cardinals give you clubs of things. So I'm just black boxing that set theory because I don't really understand it. All right, but this is a true fact. We have this unbounded set of ordinals less than lambda, for which this map pi not just restricts to G alpha, sends G alpha to G alpha, but does so bijectively. It's injective and surjective. Okay. So what this tells us is that if I have any alpha in this set of ordinals, then the restriction down to G alpha is some automorphism of G alpha, and that means it lies inside G alpha plus 1. So we'll call that element gamma alpha. Gamma alpha is this automorphism of G alpha, so it's an element of G alpha plus 1, and it's the restriction of pi down to G alpha. So yeah, so for the exact same reason as before, when we take this conjugate, if I take some element of G alpha and I conjugate it by gamma alpha, all this does is it applies the map pi, because so this conjugate here I should think of as like I of this. And we know that when I conjugate an inner automorphism by some other automorphism, I apply that automorphism inside gamma alpha. And this is the same as gamma alpha of x, but x was in G alpha, and gamma alpha is just the restriction of pi, so this is pi of x. Okay. So this is really just saying the same thing as gamma alpha is the restriction of pi down to G alpha. Okay. So now what happens if I have two different elements of C? So this was like for any element of this set of ordinals C, I have this element gamma alpha in G alpha. In G alpha plus 1. But what if I had two different elements of C? So I have my G alpha, which lives in G alpha plus 1, and I have my gamma beta, which lives in G beta plus 1. And I can think about what happens when I when I use these elements, gamma alpha and gamma beta, to conjugate elements of G alpha. So the idea there is just that if I stick an element from G alpha and I conjugate it by gamma alpha, it's the same as applying pi. And if I take an element from G alpha and I conjugate it by gamma beta, that'll also be the same as applying pi, because G alpha is inside G beta, so the conjugation is the same. So because G alpha and G beta do the same thing when I conjugate G alpha, or yeah, gamma alpha and gamma beta have the same action by conjugation on G alpha. This means that gamma alpha inverse times gamma beta is in the centralizer of G alpha inside of G beta. But everything that commutes with everything in G alpha better also commute with everything in G, just because G is inside G alpha. So that means that this is inside the centralizer of G inside G beta. But we know that that centralizer is 1 for all ordinals. So really, by the same argument that we've seen kind of already, this tells us that gamma alpha and gamma beta are the same. Same argument that appeared before when we were showing that like phi equals phi 1. Just that we have these two conjugation actions and they agree on enough elements to force them to actually be the same element. So what's happened here is that for every element of C, I've produced this element gamma alpha in one of these groups. And moreover, whenever I had two different elements of C, I produced two different elements in different groups, but one of them was a subset of the other. And so under identifications, those two elements that I produced were actually exactly the same. That's what's happened here. Okay, so we started with this arbitrary element. And what happened was we have this unbounded set of ordinals, C, and each element in C gave us this element, gave us like the same element in G lambda. So remember that G lambda, because lambda is a limit ordinal, is going to be the union of over like n less than lambda of Gn. So each of these gamma alphas and gamma betas and all those gammas live inside here at some stage. And they were all the same. So I've just produced this unbounded set C produces some element of G lambda. Okay. And so that element I'm just going to call P. All right, so remember that what P does is when I conjugate something by P, I apply pi. So if I take something in G lambda, well, remember G lambda was the union of all the previous groups. So it came from some previous group. And then conjugating that element by P is the same as applying P, is the same as applying pi restricted to an appropriately smaller group. So yeah, so for any x, pi of x lives in some G alpha for alpha in C. That's because C is unbounded. And then pi of x is the same as pi restricted to G alpha of x, which is the same as conjugating x by P. Same argument we saw before. Okay, but this was any element of G lambda. So conjugation by P is the same as pi. And that means that pi is an inner automorphism of G lambda. But pi was any automorphism of G lambda. So this map from G lambda to G lambda plus 1 is surjective. All right, so that was that's the entire proof. And there was, set theory magic right here. But besides the set theory magic, it's all quite nice. All right. Cool. So I guess I'm a little ahead of schedule, which is good. I don't have too much else to say, which is the next piece of the picture is, so we have this theorem that we just proved part of, sort of, which tells us that if we start with the centerless group, eventually this process stops. And so then the only missing piece is to show that eventually we get to a centerless group. And I didn't prepare to present that proof because I don't know, I felt that of the two proofs, this one was maybe the more interesting. The other one is fine too. It's actually quite nice, but it's maybe just kind of a little more bland. No group theory, it's all sets. So I don't know, maybe up to your preference. Right, but in any case, the other part of the picture is that, if I hopefully get the next slide, yeah. The other part of the picture is this does actually happen at some point. For any group that I start with at all, I eventually get to a centerless group. So that was proven in 1998 by Joel Hamkins. And that resolved the whole thing, that eventually start with any group, get to a centerless group, and then stabilize. And as a side note, this bound that we got from that, like, it stabilizes at this stage or earlier, is fine, but you can do fancier logic to know that it stabilizes at some point before that. Who knows? So that's nice. All right, so that's kind of the resolution of the picture. I won't prove this second theorem, but it is a nice proof, and I have if you want to look it up for yourself, it's I think the paper is just called the Automorphism Tower Problem or something like that. I have a reference at the end. So I guess here's some further results with a really interesting one. So I'll start with the bullet points. Because now we know that each of these towers stabilizes, we can just define like tau of G to be the least ordinal where it stabilizes. What's the first point where this map is an isomorphism? And some interesting results is, like, so this was our classic result from 1939. Violent, Violent. And this next result was this proof by Thomas in 85. This is like the souped up version of that proof she also presented, because it has this strict inequality here. We really just showed non-strict inequality. And there's this other, this was an argument from Joel Hamkins' 98 paper. No P there. Which is, I don't know, at that point it starts getting a little dry for me, but it's true. So you have some bounds like that. And there are some other more complicated statements you can make. Simon Thomas actually has a whole like unpublished book that's about 100 pages on his website that you can look at. It's got a whole bunch of like really fancy versions of all these statements, lots of detail, how much can you say in every particular little subcase. But some really interesting thing is in 99, like right after Hamkins published his proof, they showed that this bound of Thomas can't possibly be improved in ZFC. And the way they did that was they constructed particular groups such that the tau of G depends on the model of ZFC you're looking at. And so the details of this I don't understand. It has a non-zero amount of forcing, so I'm out of my depth. But somehow they did this, and they did it enough to show that not only is it impossible to say exactly what tau of G is going to be in all cases, but you can't improve this bound in any way. This is the best possible bound in ZFC. Okay. Okay, so that's interesting. And so regardless of all these like really powerful results, no one knows if there's any countable group with an uncountable value of tau. Could be a finite group, could be a countably infinite group. No one has any idea. All the ones we've seen so far usually terminate after like omega plus some natural number of steps. And we have a couple that are like 2 omega or 3 omega or stuff like that. But we don't have any examples of a countable group that's that has tau of G uncountable, and or a proof to the contrary. So that's kind of neat. All right, and that's pretty much all I have to say. I got just some references here. If you want to look up this stuff, I'll post these slides somewhere if you want to click the links.